last class, we briefly talked about how to find the trigonometric functions of some special angles, specifically pi over 6, pi over 4, and pi over 3, or if you prefer in degrees, 30 degrees, 45 degrees, and 60 degrees. Today we're going to continue with that, but we're going to talk about how to find trig functions of angles that are larger, like 120 degrees, or 135 degrees, or 225 degrees, right? Basically, things that couldn't be in a triangle, or at least not in the right triangle. Or really, I mean, we could go bigger than 180 degrees, which means you couldn't have a triangle either. So let's remind ourselves, how do we find trig functions of angles without using a calculator, which is what we're mostly going to be doing, right? Sometimes, like on the last homework assignment that you guys just turned in today, you need to use a calculator because we don't really have the tools to do anything else. But these special angles, we definitely want to be able to evaluate without using a calculator. So I want to find, say, cosine of pi over 3, for example. I would remember the special triangle for pi over 3, or the 30, 60, 90 triangle. So here's the 30, 60, 90 triangle. I'm going to write it in degrees because that's just the way that people usually remember it. It's 30 degrees is the smallest angle, 60 degrees is the medium angle, 90 degrees is the largest angle. A hypotenuse is 2. The smallest side opposite the smallest angle is 1. And the medium side opposite the medium angle is the square root of 3. And you can check, you should check, we will check, you don't usually check, that these side lengths do satisfy the Pythagorean theorem. This squared plus this squared equals the hypotenuse squared. It does. Square root of 3 squared is 3, 1 squared is 1, 3 plus 1 equals 2 squared, which is 1. So I want to find cosine of pi over 3. It's the odd, I almost said the opposite. It's the adjacent side over the hypotenuse. So it's the adjacent over the hypotenuse. Oh, I guess I should really figure out which angle am I looking at. Is pi over 3 30 degrees or 60 degrees? Anybody.
Could you repeat the question again, please?
Sure. Is the angle I'm trying to find cosine of, pi over 3, is pi over 3 equal to 30 degrees or is it equal to 60 degrees? Well, it's a good question. We definitely want to know. So I want to know, I'm going to multiply pi over 3 by 180 degrees over pi. The pi's cancel, and 180 over pi reduces to 60. So pi over 3 radians is the same as 60 degrees. And 30 degrees is the same as pi over 6 radians. And it really is important to be able to go back and forth between these specific values very quickly. So you really want to get it stuck in your head that, oh yeah, 60 degrees is pi over 3. And 30 degrees is pi over 6. And the way I kind of think about it is, right, pi radians is halfway around the circle. Pi over 3 is a third of that, and 60 degrees is also a third of halfway around the circle. So if I want to find cosine of pi over 3, it's the same as cosine of 60 degrees. It's the adjacent side, not the opposite, but the adjacent, divided by the hypotenuse. So that's going to be 1 divided by 2. In a similar way, right, since we've already drawn it, we could also find sine of pi over 3. That sine of pi over 3, or 60 degrees, right, is the opposite over the hypotenuse, which is the square root of 3 divided by 2. Tangent, just for the sake of doing the first 3 ones, tangent of pi over 3 is the opposite over the adjacent, which is the square root of 3 divided by 1. Nobody writes it like that. We just write it as the square root of 3. So the idea when you're trying to find any trig function of any particular special angle, we're usually going to go back to seeing what the special triangle is and using that to find things. But then we want to ask questions like, what's something like, I don't know, sine of 5 pi over 3? Well, that's a problem, right? If I want to find, let's write it in green here. I want to find sine or cosine of 5 pi over 3. Well, the problem with 5 pi over 3 is the angle is too large to be in a right triangle. Right, 5 pi over 3 is like 300 degrees. I think that's right. Let's check. 5 pi over 3 times 180 over pi. 180 divided by 3 is 60, and 5 times 60 is 300. I don't know any triangles that have a 300-degree angle in them, right? Because the angles will have to add up to 180. So how do I do this? Well, we're going to use what's called the unit circle, which I know we talked a little bit about last time. It's a circle of radius 1. And even though I'm pretty sure we say this in a later class, I feel like it's a perfectly good time to say it right now. So, and I want to try and draw this somewhat nicely. You okay, Alessandra? You worried about the unit circle? So here's my circle, radius 1, which means these 4 points are all 1 from the center. So this point here is the point 1, 0. This is the point 0, 1. This is the point -1, 0. This is the point 0, -1. And the important thing to remember here is that the radius of the circle is 1. So I'm going to draw kind of just a random line, segment, from the center to a point on the circle. And here's what we all just said. The radius of that is 1. So this length here, the radius is 1. And now I can drop, how do I want to say this? See, I knew it. I always start to get ahead of myself here. Let me say it anyway. So I can drop perpendicular here. And this triangle, I'm going to call this side length X and this side length Y. So that this point here is the point where I went over X and up Y. So this is the point X comma Y. Yeah, I knew it. I always do this. I always like, is article? No, that's not the angle pi over 4 necessarily. So here's the important thing to know here. See this angle is the angle theta. Right? No matter what you pick for theta, the radius is still going to be 1, right? I can make it this angle over here. And this length here is still 1 because it's just the radius of the circle. What I want to say, and yeah, I'm getting a little bit ahead, but again, it's okay. So is that for this triangle here, I can find cosine and sine. Sine of that angle is the adjacent over the hypotenuse, which is x over r, which is x over 1, since r is equal to 1. And cosine of that angle is equal to y over r, which is y over 1, which is just y. So what's interesting here is that we can think of sine and cosine as just the coordinates on the circle. This is cosine theta, this is sine theta. Which is what's going to, isn't sine opposite of hypotenuse there, right? Oh my God, I'm blowing it totally. Yes, Alessandra, yes, so much yes. I've done the worst thing ever. Maybe not the worst thing ever, but yeah, that's a big mistake. Thanks for catching that. Would have been the end of the world. So sine of theta is the opposite over hypotenuse, which is y over r, which is y over 1, which is y. which is certainly the way I wrote it here. Cosine of the angle is the adjacent over the hypotenuse, which is x over r, which is x over 1, which is just x. So let me say this the right way now. The coordinates x, y on the circle, if you've got an angle of theta, the x coordinate is cosine of theta, and the y coordinate is equal to sine of theta, which means that you can use the idea of the unit circle to find cosine and sine of angles that are larger than 90 degrees, even though they couldn't go in a right circle. I mean, a right triangle. Some people, not myself, like to memorize all the coordinates on the unit circle. I don't find that to be particularly useful. What instead we're going to do is we're going to use the idea of what's called a reference angle. So we're going to draw it again. And what I will tell you all is you can totally Google a reference angle, or a unit circle, which will have all of the reference angles on it. I am going to draw it for you because I do think it's worth seeing. Yeah, I can draw this pretty well. Okay, unit circle. And I want all the things, yeah. So I'm going to write angles, and I'm also going to write values. Maybe not values, maybe just angles. So let's look at the first quadrant. And I want to use some different colors here, yeah. So red will be the pi over 4 angle. Yeah, sorry, trying to make this look good so you guys can see it. So let's say, so this red angle, the angle is pi over 4 radians, or 45 degrees. All right, we've got half of 90 degrees, that seems reasonable. And then in blue, we'll have a 30-degree angle. This angle is pi over 6 radians, which is 30 degrees. And then green, we'll have the 60-degree angle, which is pi over 3 radians. Okay. And then we also have down here theta equal to 0 radians, which is equal to 0 degrees. And up here, theta is equal to pi over 2 radians, which is 90 degrees. So in the first quadrant, and this is the first quadrant, right? We're in quadrant 1, where x is positive and y is positive. These are the 3 angles, and these are your reference angles, meaning any other angle we talk about, the reference angle will be one of these angles. I should say any other special angle, because a reference angle can be any angle that's between 0 degrees and 90 degrees, or 0 radians and pi over 2 radians. Let's draw the rest of this picture. So I'm going to draw it out real quick like here. All of my pi over 4 angles are going to have a red look. This angle here is going to be 3 pi over 4, which is 135 degrees. This angle here is going to be 5 pi over 4, which is 225 degrees. And this angle here is going to be 7 pi over 4, which is 315 degrees. And here's the idea of a reference angle. For any angle that's larger than 90 degrees, you take the angle that's measured to the x-axis. And that angle is the reference angle. So this angle, which is 135 degrees, the reference angle is what you get when you measure to the x-axis, which is 45 degrees. By the way, I should point out that this angle over here is pi radians, which is 180 degrees. So from 135 to 180, oh yeah, the angle is 45 degrees. Or from 225 back to 180, the angle is 45 degrees. And from 315 up to 360 degrees, which is 2 pi radians. The reference angle is again 45 degrees, or pi over 4 radians. So here's what I want to point out. This is a pattern that becomes repetitive. For any of these angles that have a denominator of 4, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, the reference angle is always 1 pi over 4. Let's look at the blue ones. Pi over 6. So this angle over here is 5 pi over 6, or 150 degrees. And you might notice to get from here to the x-axis, it's going to take 30 degrees, which is pi over 6. Or for this angle here, which is 30 degrees away, 180 plus 30 is 210. So this angle is 210 degrees, which is 7 pi over 6 radians. I didn't draw that one very well, but such is life. This angle is also 30 degrees away from the x-axis. This angle is, well, 360 degrees minus 30 degrees is 330 degrees. So that's going to be 330 degrees, or 2 pi minus a pi over 6 is going to be 11 pi over 6. Okay, lastly, the green ones, the pi over 3s. So this angle up here is theta equal to 2 pi over 3, which is double pi over 3, so double 60 is 120 degrees. This angle down here is 4 pi over 3, which is 4 times 60, which is 240 degrees. And this angle over here is 5 pi over 3, which is 300 degrees. Okay, and again, I want to point out that this green angle measured to the x-axis, that's 60 degrees, right? 120 to 180 is 60 degrees, or 2/3 of pi to a whole pi, you're missing a third of pi, which is 60 degrees. Same deal here. That angle is 60 degrees, or pi over 3 radians. Same deal here. That angle is 60 degrees, or pi over 3 radians. So I can't stress enough that when you're talking about a reference angle for any angle, you're talking about how much you have to measure to the nearest x-axis. So if I said my angle is 5 pi over 3, what's the reference angle? Well, 5 pi over 3 measured to the x-axis, the measured angle is 1 pi over 3 radians. And the nice thing about these special angles is that the reference angle is always just pi over the denominator if you're talking about it in radians, which is cool. I think it's cool. Let's see, there's more I want to say about this. I'm going to try and leave this picture up for a minute. Yeah, I'll probably work on the side of the board. So I know this isn't in this section yet, but when you talk about a reference angle is the positive angle between 0 degrees and 90 degrees, or if you prefer, 0 radians and pi over 2 radians, that gets you to the x-axis. That is the difference between the given angle and the x-axis. So a couple examples before we start doing some of this stuff. So let's find the reference angles for the following 3 or 4 angles. So let's say our given angle was 160 degrees. What's the reference angle? Well, I'm trying to get to the x-axis. I guess I could draw a picture. 160 degrees ends about right there. How much more degrees do I need to get to the x-axis? What am I missing? All right, you guys, how many degrees am I missing? Exactly. Thank you, Mason. 20 degrees. Now, the way you could have found that if you didn't just see it is say, well, I know that the x-axis is at 180 degrees. So 180 minus 160 degrees is going to give me 20 degrees. Or what if my angle was, I don't know, 260 degrees? Now how am I going to find my reference angle? Well, again, I'm always thinking about trying to get back to the x-axis. So the question I really have to answer is 260 degrees in quadrant 3 or quadrant 4? So here's quadrant 1, 0 to 90. Here's quadrant 2, 90 to 180. Here's quadrant 3, 180 to 270. I'm in quadrant 3. So I'm in quadrant 3, right there. There's 260 degrees. And here's the thing. I've definitely seen people in the past say that the reference angle here is 10 degrees. It's not 10 degrees. 10 degrees is how far it is to the y-axis. We always have to measure to the x-axis. So to get to the x-axis, I have to go back that way. So from 180 to 260, the difference is 80 degrees. Oh, sorry, I didn't write the reference angle the previous one. So here the reference angle is, what did I say? 80 degrees. And the way we could have found that would have been by doing 260 minus 180. Oh yeah, that's 80. Or you could even go somewhere in quadrant 4. What if my given angle was, I don't know, 345 degrees? Well, then I'm almost all the way a full revolution. But how much am I missing from a full revolution? Well, a full revolution is 360 degrees, so I'm missing 15 degrees. So my reference angle here is 15 degrees. 360 degrees minus 345 degrees is equal to 15 degrees. So I really want to stress the reference angle is the measure to the x-axis. Let me do 2 more because there is another thing I want to say. You can also do them in radians. In fact, we will usually do them in radians. So if I was looking at, say, an angle of, let's make it interesting. Let's say my angle was 7 pi over 9. That's less than pi. I'm probably in quadrant 2. There's 7 pi over 9. And I want to know what's the reference angle? What's the measure to the x-axis? Well, why do we go backwards? Excellent question, Anaïs. The reason we went backwards is because we're always trying to get to the x-axis. So the problem is here, we've overshot it, but not far enough to go around to the 4th quadrant to just keep continuing on. So, right, in the 3rd quadrant, so in fact, the real answer to your question is, in the 3rd quadrant, if your angle's in the 3rd quadrant, you're going to do your angle minus 180 degrees, or your angle minus pi radians to find the difference. But in the 2nd quadrant, it's 180 degrees minus your angle. And in the 4th quadrant, it's 360 degrees minus your angle to find the difference. But in quadrant 3, it's your angle minus 180 degrees. Here, to find the reference angle, well, it's the difference between, basically, it's the difference and then it has to be positive. So you could subtract in the wrong order, but get a negative number and then just change it to a positive. That would also work. If you did 180 minus 260 and got negative 80, you'd be like, oh, my reference angle has to be positive. So here, my reference angle would be pi minus 7 pi over 9. Pi is 9 pi over 9. Minus 7 pi over 9 is 2 pi over 9. Or if my angle was, I don't know, my angle is 15 pi over 13. That's a little bigger than pi. I'm probably in quadrant 3. Again, my angle here, the x-axis angle is just pi. So I have to find this difference here. Well, from here to here, I'm going to do the bigger one minus the smaller one. 15 pi over 3 minus pi is 15 pi over 3. Sorry, 15 pi over 13 minus 13 pi over 13, which is 2 pi over 13. So the idea with reference angles is you're always trying to find the positive angle measured to the x-axis. Why is this helpful? Well, because it's going to allow us to think about what the angle would be in a different quadrant, even if the angle is bigger than an angle that could be in a right triangle. Let's look at some examples of this. So I said before, I want to find sine and cosine of 5 pi over 3. So here's what we're going to do. We're going to draw the angle. So 5 pi over 3 is in the 4th quadrant. There's kind of a trick for knowing the quadrant when it's one of these special angles. So for the pi over 3s, 1 pi over 3 is in the 1st quadrant, 2 pi over 3 is in the 2nd quadrant, 3 pi over 3 reduces so we don't count it, 4 pi over 3 is in the next quadrant, 5 pi over 3 is in the next quadrant. All the ones that don't reduce end up in the next quadrant. 1 pi over 6 is in quadrant 1, 2 pi over 6 reduces, 3 pi over 6 reduces, 4 pi over 6 reduces, 5 pi over 6 is in quadrant 2, 6 pi over 6 reduces, 7 pi over 6 is in quadrant 3, 8, 9, and 10, sorry, 7 pi over 6, 8 pi over 6, sorry, 8 pi over 6, 9 pi over 6, 10 pi over 6 all reduce, 11 pi over 6 is in quadrant 4. Same works for the pi over 4s. 1 pi over 4 is in quadrant 1, 2 pi over 4, which reduces to pi over 2, 3 pi over 4 is in quadrant 2, 4 pi over 4 reduces, 5 pi over 4 is in quadrant 3, 6 pi over 4 reduces, 7 pi over 4 is in quadrant 4. So if you're trying to figure out what quadrant and reference an angle is in, you can always be like, okay, well, how many do I count up to that don't reduce? So I'm looking for 5 pi over 3, 1 pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3 is the 4th one that doesn't reduce. So I'm going to draw that. Whoops, that was maybe a little too far. So there's my angle 5 pi over 3. And the idea is I'm going to think of the triangle with that reference angle. The reference angle is pi over 3. And I'm going to draw the triangle. Well, for this triangle, I know what the side lengths are. I know for my pi over 3 triangle, the hypotenuse is 2. Right? It doesn't have to be the unit circle. You can use whatever length you want. Right? I didn't say it was a unit circle. I'm just drawing a triangle. The side opposite the smaller angle is 1. And the side opposite the medium angle is √3. You don't have to draw this triangle. I usually don't draw this triangle. But you can. So there's 2 ways you can do this. Here's the way I don't prefer to do it. People like to say, well, I went 1 in the x direction, so it's positive 1, but I went √3 in the negative y direction, so it's negative √3. And then this is always positive. So you could say sine of 5 pi over 3 is equal to the opposite over hypotenuse, which is negative √3 over 2. And cosine of 5 pi over 3 is equal to the adjacent over the hypotenuse, which is positive 1 over 2. That's not the way I would recommend doing it, but I did want, so the reason it's negative, it's an excellent question, Alessandra, is because basically the sine value is the opposite, and the opposite is the negative thing. There's like 3 different good answers to your question, so I'm going to try and say them all. Let me go back for a second to the idea of the fact that of the unit circle, where we know that cosine and sine are the coordinates on the unit circle. Well, if I'm down here in the 4th quadrant, the y coordinate's negative, which means sine being equal to y has to be negative. On the other hand, the cosine coordinate is the x coordinate, and in the 4th quadrant, the x coordinate is positive. So in quadrant 4, sine will be negative, cosine will be positive. In fact, that's the way I usually attack this, is I like to say, here's what I know. I'm going to use the reference angle. The reference angle is pi over 3. And we know that sine of pi over 3 is positive root 3 over 2. And any angle in the 1st quadrant is going to give you a positive result. And I also know that cosine of pi over 3 is equal to positive 1/2. And then here's what we do to adjust. Because this actually isn't the angle we want to find sine and cosine of. We want to find sine and cosine of 5 pi over 3. So what do we do is say, well, I know I'm in quadrant 4. And here's the deal for the quadrants. In quadrant 1, all trig functions are positive. In quadrant 2, sine is positive. And the other 2, cosine and tangent, are negative. In quadrant 3, tangent is positive. And the other 2, sine and cosine, are negative. And in quadrant 4, cosine is positive. And the other 2, are negative, sine and tangent. And this gives us a mnemonic device, which people often say all students take calculus. All students take calculus. The trig functions that are positive in the respective quadrants are all are positive, sine is positive, tangent is positive, cosine is positive. And it's exactly because of the way the unit circle works, right? That cosine is equal to x and sine is equal to y. So over here, right, x is positive and y is positive. So sine and cosine and tangent are all positive. Over here, x is negative, which means cosine is going to be negative, and y is positive. So sine is going to be positive, and tangent is going to be negative. Over here, both x and y are negative. So cosine is negative, sine is negative, but tangent is positive. And then lastly, over here, x is positive, but y is negative. So cosine is positive, but sine is negative, and tangent is negative. So here's what I do. If I want to find sine of 5 pi over 3 and cosine of 5 pi over 3, I draw the angle 5 pi over 3, or at least I think of what quadrant it's in. That's why it's really important to get comfortable with this, to know what quadrant each angle is in, because you need to be able to know what quadrant each angle is in. And say, okay, I know that 5 pi over 3 is in quadrant 4, where cosine is positive and sine is negative. I know that sine of pi over 3 is root 3 over 2, and cosine of pi over 3 is 1/2. So that means that sine of 5 pi over 3 is equal to negative sine of pi over 3. Right? They're going to have the same value with the difference of being positive or negative. So one sec on that question, Jesus. We know they're going to have the same values because they would have the same triangles. Right? If I do the triangle for pi over 3, it's literally going to be the same triangle because it's got the same angles. It's going to be a 2 here and a root 3 here and a 1 here. So that's why this idea of reference angles works, because if you're drawing the triangle here or here, it's the same triangle. It's just that down here, some things end up being negative. Specifically down here, the y values are negative, which means sine is negative. So I'm going to find sine of 5 pi over 3 by saying, well, I know what sine of pi over 3 is. It's root 3 over 2. And since I'm in quadrant 4, where cosine is positive, that means sine has to be negative. And then for cosine of 5 pi over 3, I know it's got to be positive because again, I'm in quadrant 4. It's positive whatever the cosine value of pi over 3 was. And then we know the cosine of pi over 3 is equal to 1/2. So it's positive 1/2. So again, Jesus, the ASTC stands for what's positive in each quadrant. And the way to remember it is using the saying, the rhyme, it's not really a rhyme, the mnemonic device. All students take calculus. All trig functions are positive in quadrant 1. Sine is positive in quadrant 2, and the other two, cosine and tangent, are negative. Tangent is positive in quadrant 3, the other two, sine and cosine, are negative. Cosine is positive in quadrant 4, the other two, sine and tangent, are negative. And notice I'm not talking about the other 3, the reciprocals, cosecant, secant, and cotangent. Those all do whatever their original function is. So if sine is positive, its reciprocal cosecant is also positive. If secant is negative, sorry, if cosine is negative, its reciprocal secant is also negative. Because taking a reciprocal of something doesn't change its positive or negativeness, right? The reciprocal of 2 is 1/2, still positive. The reciprocal of -3 is 1 over -3, which is still negative. So reciprocals don't change signs, which is why we don't talk about the reciprocal functions here. So let's talk about how to use this in practice. Let's see how much time I've got. I got 10 minutes. I can, yeah, okay. I can do this. I can do what I need to do in 10 minutes for sure. Okay. So I don't want to erase this yet. It's too pretty. I mean, it's not that pretty. It's all right. Let's do, sorry, so here's quadrant 1, quadrant 2, quadrant 3, quadrant 4. All students take calculus. So we're going to use this knowledge and the knowledge of the special triangles, the 45, 45, 90, and 36, sorry, and the 30, 60, 90 triangles, to find trig functions of other values. Like I want to find sine of 7 pi over 6 and cosine of 7 pi over 6 and tangent of 7 pi over 6. Okay, 7 pi over 6, just a little bigger than pi, right? It's 7/6 of pi. So I know that I'm in quadrant 3. I'm just a little bit bigger than pi. Also, since it's my special angle, I know it's whatever number it is on the not reducing, right? 1 pi over 6 doesn't reduce. 2 pi over 6 reduces to pi over 3. 3 pi over 6 reduces. 4 pi over 6 reduces, but 5 pi over 6 doesn't. 6 pi over 6 does. 7 pi over 6 doesn't. So the third non-reduction I got to means I'm in the third quadrant. So my angle, my reference angle, is pi over 6. For rate, this is why radians, one of the reasons radians are really nice. To see the reference angle, you just look at the angle and be like, well, I should say, for special angles, pi over 6, pi over 4, pi over 3. If you see something with a something pi over 6, like I'm a reference angle is pi over 6. It doesn't work for it doesn't work for weird things like 7 pi over 9, right? The reference angle is not just pi over 9 here, it's 2 pi over 9. But for the special angles, this is kind of this neat thing that happens where you're just like, oh, if it's 7 pi over 6, my reference angle is pi over 6. Great. So wonderful, pi over 6. I'm going to draw the triangle for that. Pi over 6 is the 30-degree angle. So the opposite side is 1, the big side is 2, the medium side is root 3. So here's what I know. I know that sine of pi over 6 is 1/2. I know that cosine of pi over 6 is root 3 over 2. I know that tangent of pi over 6 is 1 over root 3, which I should really rationalize as root 3 over 3. But notice I've left myself some space because, yeah, these are the right values, except I might be off by a plus or minus. So I have to say, okay, in quadrant 3, let's see, all students take calculus. In quadrant 3, tangent is positive, which means the other two are negative. So sine of 7 pi over 6 is -1/2. Cosine of 7 pi over 6 is negative root 3 over 2. Tangent of 7 pi over 6 is positive root 3 over 3. So my advice for these problems is to find the values using the nice triangles that we have. And then after you've found the appropriate values, determine if they're positive or negative based on the quadrant that the angle is in. That's the whole kind of deal. Let's look at a couple more.
Can I ask a question first?
Yeah, go ahead.
How did you get the side lengths of the triangle?
So that's from last class. We talked about how there are two special triangles. There is the 45, 45, 90 triangle, or the pi over 4, pi over 4, pi over 2 triangle. And the side lengths on that are 1, 1, and the square root of 2. And the way we found it was we said these are the same. We used the Pythagorean theorem to find this one. For this triangle, which is the 30, 60, 90 triangle. When these are triangles you are going to want to memorize. So the 30, 60, 90 triangle, we took a equilateral triangle that had side lengths 2 and cut it in half. So that this side length is 1, and then we use the Pythagorean theorem to find the other side length, which is root 3.
So are we always going to use the 60, 30, 90 triangles for these types of problems?
Or the 45, 45, and 90. Yeah.
Okay.
So let's look at the next one. I guess I'll finally erase this picture. So yeah, if you've got a pi over 6 or a pi over 3 as your reference angle, you're using the 30, 60, 90. If you've got a pi over 4 as your reference angle, you're using the 45, 45, 90. So let's say I want to find sine of 3 pi over 4 and secant of 3 pi over 4. Okay, 3 pi over 4, I got a pi over 4. And in fact, I know that I'm in quadrant 2. I guess I don't need to think about the quadrant yet. Let's just think about, well, no, I should, yeah. I need to draw the triangle. So the triangle for 3 pi over 4, well, I know the reference angle is pi over 4, which is 45 degrees. So here's my reference angle, pi over 4. Here's the triangle, which has a 1, a 1, and a root 2. So I know the sine of pi over 4. So I want everyone to really pay attention to it. I'm not saying sine of 3 pi over 4 is equal to this. I'm saying sine of pi over 4. Sine of pi over 4 is opposite over hypotenuse, which is equal to root 2 over 2. I'm leaving space, though, for it to be positive or negative, right? I haven't determined that yet. In a similar way, secant of 3 pi over 4, well, secant is the reciprocal of cosine. Cosine of 3 pi of pi over 4, sorry, cosine of pi over 4. Cosine of pi over 4 would be 1 over root 2. So secant is root 2 over 1. So secant of 3 pi over 4 is, sorry, secant of pi over 4 is the square root of 2. Secant of 3 pi over 4, we don't know the sign yet. So I'm in quadrant 2. Because I'm definitely less than pi, I'm definitely bigger than half of pi. There's my reference angle of pi over 4. And I know in quadrant 2, sine is positive. The other two, cosine and tangent, are negative. If cosine is negative, its reciprocal secant is also negative. That's it. Okay, let's do, we got time for one more, maybe 2 more. So typically when you're given these sorts of problems, they'll be for angles that we know how to deal with. It'll be something pi over 6 or something pi over 3 or something pi over 4. But sometimes you might be given a problem. How did you conclude it was 2, you mean square root of 2, Fernanda? Because cosine of 3 pi over 4 is equal to adjacent over hypotenuse, but it is negative. So then the reciprocal of that is just, instead of 1 over root 2, it's root 2 over 1, which is the square root of 2. And it's negative. So typically for these problems, you're going to be given nice angles, or you're not going to be given an angle, like in this following question. What if sine of theta is equal to -3/5? And we also know that cosine of theta is negative. I want to find tangent of theta. All right, we have to figure out two things. We have to figure out the triangle. We have to figure out what quadrant we're in. Let's figure out the triangle. So I'm going to figure out the triangle. And when I figure out the triangle, I'm going to ignore the negative sign. I'm going to say sine is 3/5. I know, whatever, that's kind of cheating. It's not really, it's perfectly fine. Let's just say it's 3/5 for a second. So that means the opposite side is 3, the hypotenuse side is 5. And then we're going to use the Pythagorean theorem to find the unknown side, x. So x squared plus 3 squared equals 5 squared. X squared equals 25 minus 9 is 16. So x equals 4. So just using this triangle, I'm pretty sure that tangent of theta is 3/4. Well, tangent of theta is either positive or negative. 3/4. I also have to figure out what quadrant we're in. So let me ask you guys. They can't all be positive because cosine is negative and sine is negative. So this is out. Could we be in quadrant 2 where sine is positive? No. Could we be in quadrant 4 where cosine is positive? No. So by process of elimination, we have to be in quadrant 3 where tangent is positive. So tangent is positive, which means tangent of theta is positive 3/4. So that's how these problems work out. You figure out what your trig function value is going to be by drawing the triangle based on what you're given. And then you figure out the sign of it by figuring out what quadrant you're in based on what you're given. Let me do, I know it's 11:52. Let me do one more real quick because they're really fast. And I feel like you guys would benefit from seeing one more. So I'll do this next one very fast. It'll be over before you know it. Let's say I want to find, yeah. So I'm given that cosine of theta is equal to -5/6. And I'm also given that tangent of theta is positive. I want to find sine of theta. Okay, so let's draw the triangle. And I know that cosine is adjacent over hypotenuse. So cosine of theta is adjacent over hypotenuse. I'm going to say it's positive 5/6, even though I know it's really negative. So I know that the adjacent side should be 5, the hypotenuse side should be 6. And I want to find this third side, which I'm going to call y. So 5 squared plus y squared equals 6 squared. So y squared equals 36 minus 25, which is 11. So y is going to be the square root of 11. Great. Now we find sine. Well, sine of this angle is the opposite over the hypotenuse. Okay, but now I have to determine, is it positive or negative? So what quadrant are we in? We're clearly not in the quadrant where cosine, where all things are positive. because cosine is negative. And then we're given the tangent's positive, so we actually can just say, oh, hey, I know I'm over there, right? Tangent's positive. Tangent's only positive in this quadrant or this quadrant. It's not this quadrant. It's got to be this quadrant. So in this third quadrant, we know that sine is negative, so sine of theta is negative square root of 11/6. Okay,